statics.
Okay. So, good morning everybody, I'm Federico Morini, and today I'm going to show you results of the research named titanium tungsten surface alloy synthesized by physical vapor deposition and low energy high current electron beam technique, and then oxidized by plasma electrolytic oxidation. During my speech, I will present you the technique of low energy high current electron beam and also the physical vapor deposition and what happens when these techniques are coupled together, and in particular to synthesize surface alloys. Then I'm going to show you the importance of titanium tungsten and titanium tungsten surface alloys, so why we choose these materials, and then the plasma electrolytic oxidation, some information about these techniques and results on titanium tungsten oxides, and then results on the oxides and photoelectrochemical measurements that we did in order to produce some oxides that is photoactive, and then some conclusion to recap all the information that I gave to you. So firstly, low energy high current electron beam is a technique that allows the melting of the surface of materials thanks to an acceleration of electrons, and in particular it provides low energy and high current, and it helps the materials to melt in a very few layers in shorter time with an heating and cooling rate in the order of 10 to the 9 power Kelvin per second. This technique is able to modify the surface not only by melting it but also evaporating depending on the materials we work with, and it's also interesting when it's coupled with physical vapor deposition in the terms that we're going to deposit a layer of metallic materials on metallic substrate, and with the aid of this electron beam we are going to melt together both the deposition and the substrate in order to produce and synthesize a surface alloys with a graded composition, and so with different properties entering in the bulk of the material. For the synthesis of tungsten titanium surface alloys, we choose a fixed parameter in order to have a average composition, and in particular we applied for one target of tungsten with an applied voltage of 380 volts for 5 minutes. The current is also fixed at 1.5 amps, and we choose an argon pressure of 2 times 10 to the minus 3 torr in order to have a deposition with a certain amount of tungsten. After that, the samples goes under the electron beam, and we also in this case choose certain parameters in order to alloy the two metals, and we choose 30 kilovolts for 50 pulses in order to provide the melting of the tungsten that has a high melting point, with a frequency of 0.2 Hz. Also in this case we choose a defined pressure of the argon gas inside the chamber that is equal to 2 times 10 to the minus 4 torr in order to provide an amount of energy that is able to mix and alloy the two metals that we measured before experiments, and is equal to 5.4 joule per centimeter square. Titanium substrate before the treatment with the PVD and low energy high current electron beam underwent also to chemical and electron beam pretreatment in order to purify the sample itself. Chemical pretreatment was done in an etchant bath of hydrofluoric and nitric acids in order to remove from the surface of the sample possible contamination like oxides or carbides that could be possible deposited during time. But the problem of chemical etching is that it's going to produce rough and discontinuous surface. So in order to have a smooth and continuous and more homogeneous surface, we did an electron beam treatment with low energy current electron beam gun for 25 kilovolts and 10 pulses in order then to smoothen and also to remove from the inner part, inner layer of few micrometers, some possible contaminants and inclusion that could be present. And so after this pre-treatment, we did our PVD deposition and a low energy high current electron alloying in order to produce at the last step a surface alloy that has a thickness around 5 micrometers with a graded composition from the surface to the bulk of the material. We choose to study titanium tungsten alloys because from literature it shows very interesting properties in terms of mechanical behavior and also other things. In particular, from literature we noticed that tungsten could bring to titanium and higher mechanical properties and better mechanical properties and also better corrosion resistance and also a higher melting point. This is concerning the bulk materials, so the bulk alloy. We wanted to focus on the surface alloys just to have these properties on the top of our samples. And also because low energy current electron beam could bring different features to our materials, such a higher content of tungsten in the surface, so with more deeper increasing the properties like a better mechanical properties, but it also helps to produce and synthesize materials with metastable phases due to the fact of high rate of cooling and heating the materials, and also the possibility of have a grain refinement of our surface. And in that, I wanted to highlight the average composition of the alloy that we synthesized with the previous parameter that I explained, with a certain amount of tungsten and also certain voltage applied to the electron beam. From results, immediately we noticed that our materials show characteristic features of surface alloys. In particular, from X-ray diffraction was possible to notice that there was a formation of a BCC structure that is typical of titanium tungsten alloys, and in particular we form a beta titanium tungsten surface alloys. And also we noticed that this is a surface alloy because there's the presence of some peaks of the bulk, titanium bulk, HCP. And from the position of these BCC peaks, we calculated the average content of tungsten, because this peaks is shifted from the original position, and from the final position we take the value of 14 atomic % of tungsten, thanks to the deposition of 180 nanometers of the materials on titanium. From morphological point of view, we analyze both with optical microscope and scanning electron microscope, and we notice different features. In particular, thanks to this treatment, we have the formation, unfortunately, of some craters due to a high number of pulses, because we continuously stress the material to be melted and solidified, and so there's the possibility of ejection of some inclusions or contaminants forming this kind of defects. But going deeper with magnification, we notice that the situation is more smoother and homogeneous, with the formation of some cracks due to the thermal stresses that the materials undergo. But this is not a problem for applications and for other properties, because from a mechanical point of view, we tested the materials with microindentation test in order to evaluate mechanical properties. And immediately, from micro-hardness point of view, we noticed that titanium tungsten surface alloys showed a very increased hardness, in particular when the applied load to microindentation is low, so we are in the range of high tungsten content. And in particular, micro hardness goes from initial values of 250 HV, going at the final results of titanium tungsten of 1200 HV. So we almost increase the hardness of 6 times. And another interesting behavior is that the hardness tends to decrease by increasing the applied load of microindentation. So we are going to a domain of titanium, so we're going to don't feel anymore the presence of tungsten, and we feel only the presence of titanium. And so at high loads like 500 millinewton, we are going in the same value of the initial condition. Different things is about the elastic modulus. Elastic modulus of our surface alloys is low for all the applied loads as a result of both the presence of tungsten and also for the low energy high current electron beam. Low energy high current electron beam also reduced the elastic modulus of the initial titanium from the etching to the low energy high current treated. And also with the titanium tungsten surface alloys, we have a lower average value of 90 gigapascal that is classical of this treatment and this material. And after the synthesis and characterization of these surface alloys, we did an electrochemical treatment in order to synthesize oxides. And in particular, we choose plasma electrolytic oxidation because we studied before with titanium and titanium dioxide. And this is a very interesting technique in order to produce nanostructured, in particular nanoporous oxide that could be photoactive in a very short time when it compares to normal anodization. This happens because we applied higher voltages compared to classical anodization, and usually we did with titanium dioxide, and the phase that we could synthesize is anatase and rutile that has 2 different precise band gap and make titanium active under UV irradiation. As concerning tungsten and tungsten oxide, usually it is synthesized with anodization or with doping. So it's like a precursor inside a solution. And we wanted to study the plasma electrolytic oxidation on tungsten trioxide to see if it is a possible route instead of using as a dopant. And because among all the possible oxides of tungsten, tungsten trioxide is the most interesting from the photocatalytic point of view because it showed a lower band gap and also shifted band gap that makes it more active in the near visible irradiation. So we did the plasma electrolytic oxidation on these materials using a sulfuric acid 1.5 molar solution with an initial temperature of 0 degrees and for 5 minutes by applying a voltage from 100 to 200 volts with a step of 20 volts per sample. And from results, was possible immediately to see that there's a behavior that is changing by increasing the voltage, and in particular by applying 100 volts to the PEO, there is the formation of anatase and some tungsten trioxide with also the presence of signal from the substrate because this oxide is very thin and also it's sensitive to the substrate. While by increasing the cell voltage of the plasma electrolytic oxidation, it's possible to increase the thickness of the produced oxide and also the possibility to have different phases. So by increasing it, titanium dioxide is no more present in forms of anatase, but is forming rutile that is typically formed at higher voltages, with also the presence of peaks of tungsten trioxide. Another interesting things taken from this X-ray diffraction patterns is that both rutile and anatase peaks is not centered in the original position but is shifted, and this is shifted due to the presence of both tungsten and tungsten trioxide. And in particular, we have that anatase tends to increase its volume of the cell by increasing the voltage, and the rutile tends to decrease its volume by increasing also in this time the voltage. Both of these features, so the changing of the volume of the cell, so having a distorted anatase and distorted rutile, and also the presence of tungsten trioxide, will be interesting from photocatalytic point of view. From morphological point of view, we have these ADS and SEM images that shows that by increasing the cell voltages of the plasma-electrolytic oxidation, we have a changing in the morphology. In particular, by increasing it, we have a more dishomogeneous and irregular coral-shaped structure, while at low voltages, nominally 120 volts, we have the typical nanoporous sponge structure. Comparing it to the classical titanium dioxide produced with the PEO, we have already at 140 volts a formation of coral-like structure, while titanium usually show the sponge-like structure until 160. So also in this case we have a change. Another things that we notice from EDS analysis is that by increasing the plasma-electrolytic voltage, the tungsten content in the oxide tend to decrease. In terms that is more dispersed inside the oxide, and goes from 3.2 atomic percent to 0.3 atomic percent. But when we have tungsten, and also in this image, there is also the presence both of titanium and oxygen. So we have the production of tungsten trioxide or a mixture of oxide system. At last, we did some photoelectrochemical measurements in order to see if our oxides is active under some radiation, and in particular we did linear sweep voltammetry measurements from minus 1.5 to 3 volts with a scanning rate of 1 millivolts per second in a 4 millimolar KCl solution. And we wanted to test both the material under UVC irradiation and under UV visible irradiation to see the behavior and comparing it to the titanium response under the same irradiation. In order to do that, we tested both with the light on and also the light off and measured the photocurrent. The distance between the lamp and the sample is fixed in order to know and have the precise value of irradiation and the emissivity of the lamp. From results of the photocurrent under UVC irradiation, we immediately see from these graphs that the titanium dioxide system has a higher photocurrent response almost for all the voltage of the PEO, while titanium tungsten mixed oxide has a lower behavior and lower photocurrent. And talking about numbers, we had calculated the photocurrent at 0.5 and 1.5 volts, and we noticed that the most active materials for titanium oxide is the one produced at 140 volts, while the titanium tungsten oxide show very, very low value at the same cell voltages. An interesting thing of titanium tungsten oxide system is that it became more active when it was synthesized at 160, 180 and 200 volts. And particularly 200 volts show higher values, almost the same of titanium oxide, while titanium oxide is almost zero, null photocurrent. And same things, different but same. We have results that is higher for titanium tungsten oxide under UV visible in terms of photocurrent, while titanium oxide has lower photocurrent. And also in this case, in terms of number, we have almost the same behavior, that we have the best photoactive materials at 140 volts for titanium oxide, and lowering to 200, while in the case of titanium tungsten oxide system, we have more active materials at 160, 180, and 200 volts. And in this case, in particular, the 200 volts is even more active than titanium dioxide, and while also 160 show almost the double value of photocurrent compared to the one of titanium dioxide. This is due to the fact that tungsten is usually produced from literature at higher cell voltages, so when we synthesize tungsten trioxide and titanium dioxide at 200 volts, we are starting to produce a more active and more present tungsten trioxide. If we're going to increase more the cell voltages of the PO, we are going to produce more tungsten trioxide that will be more active under UV visible light. And to conclude and summarize my speech, we synthesize titanium tungsten surface alloys with low energy high current electron beam coupled with the physical vapor deposition, and we notice that we have the beta titanium tungsten phase with an average content of tungsten in the alloy of 14 atomic percent. And these alloys show a very increased micro hardness at low applied loads, reaching 1135 HV, and also low elastic modulus for all the applied loads with around value of 90 gigapascal. As concerning the plasma electrolytic oxidation and the mixed oxide system, we synthesized a system of titanium dioxide and tungsten trioxide with an average content of tungsten in the oxide that goes from 3.2 to 0.3 atomic percent. And from photoelectrochemical measurement, we noticed that tungsten trioxide redshifted the light absorption, so is more active under UV visible light. And in particular, current values, we noticed that under UVC radiation, this mixed oxide system show a better photocurrent when it's synthesized at 200 volts, while under UV visible irradiation, it shows better results when it's synthesized from 160 to 200 volts, reaching also value that is double the one of titanium dioxide. And thank you for your kind attention.
Thank you. Very interesting.